Hello everyone. So my name is Wei, and it is my great pleasure to be here to briefly talk about our recent work, confusion matrix design for downstream decision making. So this is a joint work with my colleague Yiding Feng from Hong Kong University of Science and Technology, and I am a faculty member of the Chinese University of Hong Kong. So the motivation of this work is coming from the practical applications where the machine learning predictions or AI algorithm predictions can be used for the downstream decision makings. Let me give you some concrete examples. Consider this criminal justice scenario where the algorithms, for example, the compass system, can provide the predictions of the defendant's likelihood of real offending to help the judges to make their bail decisions. And in healthcare areas, the algorithm can also provide the disease predictions of the patient to help the doctors to make their clinical decisions. So if you think about this machine-in-the-loop decision-making scenarios, there are two parties. One party representing the AI and the machine learning designer, and another party representing the decision makers like the judges or doctors. So the AI and the machine learning designer can provide the predictions about the underlying true outcome. For example, whether this defendant is guilty or not, and whether this patient has disease or not, to help the downstream decision makers, like the doctors or the judges, to make the downstream decision makings. And the decisions made by the decision makers not only affect the decision makers' payoff, but could also potentially affect the AI and the machine designers' payoff. And of course, there are many challenges behind this interaction process. For example, the AI designer cannot always be able to provide perfect predictions. And the predictions they provide are really inaccurate, for example, subject to some type 1 or type 2 errors. And these errors are really coming from the fact that the AI designer have limited data access or have limited access to the computational resources that they can never learn the true outcome of the underlying data. And also, all the predictions provided by the AI algorithm are often subject to some additional considerations, like the fairness concern or fairness constraint or privacy constraint. And in the meantime, there exists a preference misalignment between the AI designer and the decision makers. The AI designer may favor of some particular decision, where the decision makers may prefer to make other decisions. So in this work, we provide a general framework to study how should the AI designer design the predictions for the downstream decision making. And in particular, we use a confusion matrix to capture the informativeness or how accurate of this prediction is. And we build a connection between this AI designer's confusion matrix design problem and a classical framework in economics literature called the information design framework to try to understand how to provide predictions to the downstream decision making. And we provide algorithmic solutions to compute the optimal confusion matrix. And we allow the preference or misalignment between the AI designer and the downstream decision makers. Before I jump to our main results, let me briefly talk about how the decision maker makes the decisions when they are providing some predictions. So in practice, the decision maker not only observe the predictions provided by the AI algorithm, they are really informed how accurate or how informative of this prediction is. And typically this informativeness of the prediction or the accuracy of this prediction is given by this confusion matrix. So for example, in a binary outcome prediction task, this confusion matrix completely specifies the type 1 error, type 2 error of the prediction. And in this work, we consider the high-stake decision making. So the decision maker are Bayesian in the way that they initially have a prior belief about the underlying true outcome. And they are Bayesian in the way such as they can infer a Bayesian posterior about the underlying true outcome when they are provided by some predictions output from the AI algorithm. And the decision maker's preference is captured by the decision maker's utility function, which depends on the decision maker's decision and also the underlying true outcome. And we assume the decision maker is rational in the sense that the decision maker is able to take the actions that maximize expected utility given the updated Bayesian posterior. And as I mentioned, the confusion matrix here is not an inanimate object. It is actually can be designed by the AI and the machine designer. And moreover, the AI and machine designer can have access to the multiple data that is realized from a data distribution. And the machine designer needs to provide predictions for each of these data instances. And as I mentioned, the machine designer may have different preferences compared to the decision maker. And the designer's preference is captured by a different utility function, which also depends on the decision maker's action and also the underlying true outcome. And we'll assume there exists a common prior for a particular instance for the same data instance between the AI designer and the decision maker. And we consider heterogeneous setting in the sense that the decision maker and AI designer share a common prior for a particular data instance, but this prior for different data instances could be different. For example, in the healthcare areas, the patient's profile are different, and both the doctor and the algorithm designer can observe the patient's profile, but may hold the different prior distribution, prior belief if the different patients have different profile. And in this work, we stand from the AI designer's perspective, and we aim to understand how should the AI designer design a feasible confirm matrix to maximize her expected utility. So here, by feasibility means that we consider two practical feasibility constraints on the confirm matrix. The first one is a post-processing constraint, which aims to capture the fact that the AI designer may not be able to retrain the model from scratch, but they are able to generate the predictions based on a pre-trained model. And they can only generate the predictions by post-processing this pre-trained model. And the ROC constraint aims to capture the fact that the designer is able to retrain the machine model, but subject to some inherent uncertainty of the limited data or limited computational resources. And these ROC constraints are also motivated by the fact that the AI designer may also need to satisfy the additional considerations like the fairness consideration or privacy consideration. So now let me briefly talk about what is a post-processing constraint confirm matrix. So this constraint is specified by an initial confirm matrix that captures the accuracy of a pre-trained model. And under this constraint, the AI designer can only generate predictions by remap the outcome or the predictions for output from this pre-trained model to another set of outcomes. In other words, the machine learning model cannot be, the AI designer cannot retrain the machine learning model. And any feasible confirm matrix in this set contains any confirm matrix that can be generated by this post-processing procedure. And to give you some simple example, let's say like the AI designer simply use the output of the pre-trained model as their predictions, then this confirm matrix will be exactly same as the initial confirm matrix, say they are here. And we can also have a geometrical interpretation for this post-processing constraint confirm matrix. Suppose you consider a binary outcome predictions, and in this sense, the confirm matrix will be given by this 2x2 matrix, which captures the type 1 and type 2 error of your prediction. And it can be proved that any feasible post-processing constraint confirm matrix is in this shaded region. And any point in this area can be implemented by a post-processing procedure on the initial confirm matrix C0 here. And so unlike the post-processing constraint, where the AI designer is not able to retrain the machine learning model, So ROC constraint allows the AI designer to retrain the machine learning model. But we'll abstract out this process, and we assume that this training process is subject to ROC constraint in the sense that there exists ROC function that captures the inherent uncertainty of the training process. In particular, any feasible confirmed matrix given this ROC function must satisfy that the one-mass type 2 error must no larger than the ROC function value at the type 1 error here. So the motivation of this ROC constraint is coming from the fact that in some scenarios, the AI designer is able to train the machine learning model again, but subject to some inherent uncertainty due to the limited training data. Or additionally, you can also think about this ROC constraint also captures a certain scenario, such as the AI designer needs to satisfy, let's say, privacy considerations. For example, we can prove that to make sure the predictions to satisfy the differential privacy, then this confirmed matrix will satisfy this linear constraint here. Okay, great. So having talking about the feasibility of the confirmed matrix, so we are now ready to formally write down the AI designer's problem. So we can actually write out AI designer's program. And so the objective here is the AI designer's expected utility when choosing to use a confirmed matrix. And here the constraint captures the feasibility of the confirmed matrix. And A star here denotes the decision makes optimal decision given the provided prediction Y hat here. And you may be noticed that if we think about the confirmed matrix as an information structure that provides the information about the underlying true outcome, and the Y hat as the information signals that carries over the information about the underlying true outcome, then we can connect the AI designer's confirmed matrix design problem to this public persuasion problem with heterogeneous priors. So here the heterogeneity does not mean that the AI designer and the decision maker has a different prior. It means that they share the common prior for the same particular instance, but this prior could be different for different data instances. And for the post-processing constraint here, this public persuasion captures stating that the AI designer cannot fully observe the underlying state. It is subject to some initial accuracy constraint of the given by the initial confirmed matrix C0 here. And the ROC constraint here captures the scenario that the information structure needs to additionally satisfy some ROC constraint. So there have been a few works talking about how to design optimal information structure in this public persuasion setting, but they are more focusing on the heterogeneous utilities, such as for each data instance, the AI designer and the decision maker have different utility functions. And the main results they establish there is that it is usually computationally hard to compute the optimal information structure. So the main results in this work is that for the post-processing constraints matrix, confirmed matrix set, we show that under a met condition for the underlying data instance priors, there exists an efficient linear program to compute the optimal confirmed matrix. And for the ROC constraint problem, there exists an efficient algorithm to solve the optimal confirmed matrix. Okay, so in the remaining of the talk, let me briefly talk about how we obtain these algorithmic solutions, especially for the post-processing constraint. So to give you some intuitions, let me first focus on this binary outcome prediction task. So under this binary outcome task, we can see that each data instance, the prior for each data instance, can be represented by a scalar value that representing the probability for this outcome to be the outcome 1, right? And in this scenario, we can show that there exists a downward isolated property for this problem. In particular, for any confirmed matrix and for any predictions provided by the AI algorithm designer, If the decision maker's optimal decision under a particular data instance is taking the decision one, then the decision maker's optimal decision under another data instance, as long as this data instance has a larger prior, this decision should still be taking the decision one. Okay, so with this downward IC property, we can also show that any feasible configuration matrix can be induced by designing a signaling policy that prescribes the conditional probabilities on sending which signal to the decision maker conditional on the realized prediction. And meanwhile, this signaling policy needs to additionally satisfy this downward IC property. So with this observation, we can actually express the AI designers, reformulate the AI designers problem as this linear program. And this first constraint represents the downward IC property here. Okay, so for the general number of outcomes, you may be wondering if we can still have these properties. And unfortunately, the downward IC may not hold for when the outcome space is beyond the binary, but it actually holds with this by the condition on the data instance prior. So as long as the underlying data instance distribution satisfies this increasing monotone likelihood ratio, then we can show that there still exists a downward IC property in our problem. In particular, the decision maker's optimal decision under a particular instance is taking decision one, then there exists order of the data instance such as for any data that is larger, for any data instance that has an index larger than this I here, the decision maker's decision is still taking the action one here. So this downward IC property it actually holds for this binary outcome space because you can simply sort the data instance in the increasing order of their prior. And for the general number of outcomes, it is also a commonly made assumption in the constraint design literature, field division literature, and also classification. And it is also a common assumption made in the economics literature, like the information design and also rational inattention literature. Okay. So with this condition, we can show that for any initial given config matrix, there exists a linear program that has a polynomial size of the number of data instances and the number of outcomes to compute the optimal confusion matrix. So let me use one last slide to briefly talk about how we solve this confusion matrix design problem when the AI designer is facing this ROC constraint. So recall that the ROC constraint is specifying the convex inequality over this type 1 and type 2 error. So for this type of problem, we will explicitly focus on this binary outcome prediction task. So now you may be wondering whether we can also optimize this confusion matrix while reformulating as a signaling policy. And unfortunately, it is unclear how to include this ROC constraint because ROC constraint is operating on the type 1, type 2 error, but the signaling policy is operating on a set of signals. And you may be also wondering whether we can just directly optimize this signals objective over these two variables because it type 1 and type 2 error. But it turns out this signals objective is non-convex and non-continuous. So the key idea here is that we can, since we are still in the binary prediction task, we still have this downward IC property, and we can iteratively optimize the signals object, the AI designer's objective, subject to the downward IC constraint on a particular data pair. And then we can iteratively solve the optimal data pair to find out the optimal corresponding configuration matrix. So here, the first two constraints captures the downward IC constraint for the particular data pair, and the second constraint is a convex constraint specified by the ROC curve. And by doing this, we can show that this is a convex program, and we can have a set of convex programs to solve the optimal configuration matrix under this ROC constraint set. So to summarize, in this work, we studied this computer matrix design problem for downstream decision making, and we connected it to the public persuasion with heterogeneous priors. And here the heterogeneity comes in from the AI designer and the decision maker have a priors that could be different with different data instances. And we consider two natural constraints. The first one is a post-processing constraint. And we show that under by the condition of the data instance distribution, there exists an efficient linear program to solve the optimal computer matrix. And we also consider this ROC constraint. And for binary outcome prediction task, we show that solving the optimal computer matrix can be solved by a set of convex programs. And there are also many interesting open questions, in particular for the multiple outcomes. If we do not make any assumption about the data instance prior, can we show that it is unbehind to solve the optimal computer matrix, both for the post-processing and ROC constraint problems? And also for the general number of actions, what are reasonable conditions that we need to ensure that there exists a polynomial time algorithm to compute the optimal computer matrix. So that's all about my talk. If you have any questions, please send me an email. Thank you.